to Sangjun. He is from the Polytechnic Institute, and he'll be presenting on the attack resilient vehicle platooning.
Okay, can everyone see my slide?
Yep.
Okay, let me start. Hello, everyone. This is Sangjun. I'm a PhD student from the Department of CIT. Today, I'd like to present my research on secure vehicle platooning against cyber attacks using distributed nonlinear model predictive control. In this presentation, first, I will give you the fundamentals of vehicle platooning and research objectives. Then I will talk about the proposed method and validation of it. Vehicle platooning is an important and autonomous driving method that allows a group of vehicles to travel together in a safe and efficient manner. This is potentially so efficient that it saves on fuel, reduces pollution, and helps control traffic flow. And an obvious benefit is that it prevents accidents caused by human error like driver fatigue. However, the communication channel that enables each vehicle to exchange driving data among vehicles is inherently vulnerable to cyber attack. To explain more generally, these vehicles communicate each other and maintain inter-vehicle distance and relative speed. Thus, there are two control objectives to achieve: speed control and distance control. For example, in case of the second follow vehicles, the goal of the speed control is to accelerate its speed to track the leader's speed when the distance between the first and second vehicle is larger than the desired safe distance. And the distance control is to maintain the desired safe distance when the distance between the first and the second vehicles is smaller than the desired safe distance. In this way, a group of vehicles can travel together while maintaining distance and speed. The vehicle platooning is highly susceptible to security attack, and it can lead to catastrophic load collisions and string instability in traffic, causing severe degradation in the efficiency. For example, there are two groups of 6 vehicles traveling a straight road, one without attack and the other with an attack at the third vehicle. An intruder sent corrupted signal, causing the third vehicle to overspeed while other vehicles travel at a constant speed. As can be seen in the simulation, the third vehicle bumped into the second vehicle and the overall platoon is failed. So two research questions naturally arose here. So what when make the platoon unstable, and can the platoon recover itself? So to seek the answers to these questions in this research, we propose an attack resilient control scheme that continuously monitors for anomalies caused by adversary actions and adapted to the abnormal situation so that overall system continues to satisfy its goal, thus mitigating the impact of attacks. So this is an overview showing the key features of the proposed method that comprise 2 components, namely the attack detection subsystem and the attack resilient control systems. The attack detection subsystems uses a mix of non-parametric method, namely Gaussian process, and parametric method, unscanted Kalman filter. And then the attack resilient control system is designed based on nonlinear model predictive control. In this way, the proposed solution provides real-time resiliency against a comprehensive set of attacks, including spoofing, message falsification, and denial of service attacks. We consider a homogeneous platoon consisting of a leader vehicle and n number of follow vehicles. The dynamics of each vehicle can be represented as the following discrete time linear system with state vector and output vector. So talking about the attack model, the adversary is assumed to be capable of compromising a vehicle using one of these 3 types of attacks. First, we assume that there is an unauthorized intruder who is able to take the control of ith vehicle and induce a constant offset to each current acceleration command when an attack begins at t delta. Second, an intruder is capable of simultaneously listening sensor readings among vehicles and sending falsified messages to a target vehicle. Specifically, specifically, the intruder is able to listen the position sensor readings of ICE vehicle and manipulate it by adding delta falsification to its current position. Lastly, an intruder introduces the network to overwhelming fake requests. This unacceptably high network traffic causes packet loss, which disables the network from responding to legitimate request sent by the authorized users. This attack blocks the directional communication link between a target vehicle and its neighbor, preventing the JAIF vehicle from receiving state information of the ICE vehicle during the attack period. The main advantage of using a mix of GP and UKF is that GP regression enables UKF to become independent from the uncertainties of models. The GP regression provides the statistical properties that describe an unknown function from a given set of training data. Therefore, the proposed method does not depend on the availability of parametric prediction and measurement models, which are inherently vulnerable to attacks. Thus, the GP-UKF integration provides the GP regression model of the state transition function G with the corresponding covariance Q and the GP regression model of the measurement function H with the corresponding covariance R. The predicted states are then applied to the proposed attack detection algorithm in the following. So now the predicted state and actual sensor measurement are used to compute the residual vector, which captures the deviation as potential attacks. This residual vector applied to statistical testing called chi-square detector, and it determines whether to activate the attack resilient control or not. Thus, the detection algorithm continuously compares the residual with a given threshold, which is determined from the chi-square table corresponding to the desired confidence interval and the degree of freedom. And finally, it triggers an alarm and activate the proposed attack resilience system if the condition is satisfied or violate due to an attack. If an attack is detected and identified in the previous step, each vehicle starts computing its own optimal control input by minimizing the cost function while satisfying the sixth constraint. The key of achieving this distributed attack resilient nonlinear model predictive control, called DAR NMPC, is to satisfy the last two terminal constraints. The first terminal constraint is to enforce the vehicle I under attack to have the equivalent output as the average of assumed output. And the second terminal constraint is to enforce the vehicle I under the message falsification attack to travel with a constant speed at the end of the prediction horizon. In practice, this optimization problem can be solved using conjugate gradient method. So by solving it, its vehicle achieves the speed and distance control objectives in the present of attack. So talking about the validation of the proposed method, we predict the nonlinear state using the GP-UKF state estimation. In the first figure with a set of 100 data, the GP-UKF in yellow solid line predict consistently the true state in black dotted line. The gray area indicate thrice the standard deviation of the state estimation, and the blue dots show the training data point. In the second figure, the GP-UKF performs relatively small estimation error than other vehicles, extended Kalman filter and unscanted Kalman filter alone. In addition, we compute the Mahalanobis distance between the ground truth and the mean of estimation error for each filter. The results indicate the GP-UKF outperform other filters in terms of estimation error. In general, the UKF produce equal or better performance than the EKF, where the improvement over the DKF depends on the state uncertainties and the nonlinearity in G and H functions. So this is mainly because UKF perform the linearization of the functions G and H by a stochastic approximation, while EKFs apply Taylor series expansion around the most recent estimate. So based on the GPUKF prediction, the statistical testing is performed and each attack is detected where the residual of the vehicle tree significantly exceeds the threshold, while other vehicles follow a similar pattern of Gaussian noise. This can be expected since we assume that the GPUKF models have additive Jermain Gaussian noise, so that the evolution of the residual vectors are also Gaussian-like. In case of denial of service attack, no significant deviation is observed in the evolution of the residual vector. This is mainly because the denial of service attack sabotages the communication link, which is not measured through the GPUKF detection. However, this attack is able to be detected by investigating data exchange conditions. Now we perform extensive simulation using a custom driving environment in MATLAB. We consider a platoon consisting of a leader vehicle and 5 follower vehicles. The leader vehicle starts traveling at 25 meters per second for 1 second, then it accelerates until reaching 28 meters per second and keeps this speed at the end of the simulation. Each follower vehicle also starts traveling to track the leader's desired speed while keeping the desired safe distance each other. We consider 3 different attack scenarios according to the attack models previously mentioned. So for the spoofing attack scenario, 5 acceleration offset begins at the vehicle tree at 4 seconds. As can be seen in the retro view of platooning, the attack causes the third vehicle to accelerate, but the attack resilient control is immediately activated to mitigate the attack, slowing it down to avoid any possible collision. Finally, there is no collision and each vehicle reached the destination safe and sound. In case of message falsification attack, the intruder sends additive 20 meters of falsified message to the position sensor readings of the third vehicle at 4 seconds, making it believe that there is only 10 meters apart to the vehicle ahead. This attack causes a sharp decrease in the speed of the third vehicle to avoid any collision expected. However, as soon as the DAR NMPC starts generating new control signals, it effectively mitigates the negative effects of the message falsification attack. And all the vehicles keep the desired safe distance and then speed at the end. Lastly, the denial of service attack prevents the third vehicles from receiving the desired speed and distance data of the second vehicle. As soon as the attack is disclosed, the third vehicle is forced to make use of the most recent updated data prior to the attack activated. This deceives the third vehicle into accelerating the speed during the attack period, even if the safe distance is significantly violated. However, the DAR NMPC mitigates the attack shortly after the attack was rejected and the speed and the inner vehicle distance starts returning to its original state. As a summary, in this study, we developed an attack-resilient architecture for vehicle platooning. First, Gaussian process and the unscanted Kalman filter-based attack detection scheme was proposed, and then an attack-resilient controller was presented using nonlinear model predictive control approach. Extensive simulation results demonstrate resiliency against the 3 types of attacks. In conclusion, the proposed distributed attack resilient NMPC improved security and optimal efficiency in the presence of attack. Nonlinear model predictive control approach can be effective in the proper situation like this. However, they still have limitations that need to be considered as a future direction. For example, there was a trade-off between computational cost and performance. If we select more number of prediction horizon for better performance, it requires more computational cost, therefore causing delay on solving optimization problems. Lastly, I'm currently working on experiments using ground vehicles to demonstrate the efficacy of the proposed solution. This work was supported by the US Department of Justice. Thank you.